Our project is designed for cycling-focused athletes so that they can see their performance data in real time. The metrics that our project presents are velocity, power, cadence, temperature, elevation, and distance.
First and foremost, the sensors must be accurate and work reliably. The sensors made must not bother the rider nor affect their performance. Must be easy and not a hassle for the rider to use. The sensors must be cheaper than commercially available options.
Our project needed some way to display the bicycle data in real time. Our display had to be affordable, minimize the amount of space we used on the bike, and reduce the amount of hardware and wires we used overall. To solve these problems, we decided to create an application that uses smartphones, as most people already own one and they have wireless capabilities. For our application, it was written in the Swift programming language, and we used the latest version of Xcode software. This meant that our application was compatible with all iOS devices. When determining the phone location on the bicycle, our group wanted to display the data to the rider in real time. This data is essential to the rider, so it had to be available in an easy to see and access location. For these reasons, mounting the phone to the middle of the handlebars provided our group with the ideal location that provided visibility to the rider and aesthetic appearance and did not inhibit the rider in any way. Following the constraint of reducing wires and hardware space, our project uses the ESP826601 Wi-Fi compatible microcontrollers. The microcontrollers used have the ability to create a web server and act as a router for the smartphone to connect. The smartphone then connects to the web server, where it will perform GET requests to retrieve the data. Our application repeatedly performs the requests in order to provide the data in real time. Finally, the application formats and presents these metrics, emphasizing the data most important to the rider. Our project calculates velocity, elevation, temperature, distance, power, and cadence. In order to save money and produce cheaper accessories, we are calculating these metrics ourselves using sensors and microcontrollers along the bicycle. All 6 metrics are calculated on the bicycle, but power and cadence specifically must be calculated on the rotating crank arm, making it impossible to connect wires to components. To resolve this problem, we set up 2 Wi-Fi compatible microcontrollers on the bicycle to communicate. The client microcontroller is located on the crank arm, and the server microcontroller is located on the fork of the bicycle. The server microcontroller is located on the fork to be in close proximity to the wheel. So the client microcontroller sends power and cadence data to the server microcontroller, and the server microcontroller sends all data to the phone.
Powering the microcontrollers. Since our microcontrollers are on board the bike, we needed to create a battery system that was small enough to fit on the bike as well, especially where the microcontrollers were positioned. We found a 3.7 lithium-ion battery that was small enough to fit on the crank arm of the bike and the fork of the front wheel to power both of the microcontrollers. But the microcontrollers are powered off 3.3 volts, so we needed to step down the voltage of our battery. We chose to use a buck regulator. But with a buck regulator, it only works if the input voltage is significantly higher than the output voltage. In our case, our buck regulator only turned on around 4.5 volts. So we had to add a boost regulator to the out point of the battery to step its voltage up to 5 volts. That way the buck regulator could accurately step down the voltage to 2.3 volts for the microcontroller. Additionally, the boost converter circuits had charging capabilities on board. If they had micro USB ports that you charge the battery without having to take it off the bike or replace the battery itself. Here's a representation of our battery system, how it looks kind of on the bike. We have our 3.7 micro battery connected to a 5-volt boost converter, and that output is then tied to the buck regulator. So we can get 3.3 volts to our microcontroller.
To design the speedometer, a magnet was put onto the spoke of the wheel, and a Hall effect sensor was put on the bicycle's fork. But why did we choose these components? As you can see, the magnet turns the LED on when it's near the Hall effect sensor. Hall effect sensors can detect magnetism. While the magnet is rotating on the wheel, it will pass by the Hall effect sensor and the voltage will go low, indicating that one revolution has been completed. Measuring the time between revolutions gives us RPMs. With a known diameter, the distance traveled in one revolution is the circumference. With the distance and time known, velocity can be calculated and converted to miles per hour. To test the design, I did my best to keep up with a moving car with a known working speedometer and compare our results.
When designing the elevation change sensor, we decided to use the MPL 3115A2 barometer. Why did we choose this component? This barometer was cheap, fairly accurate, and could detect atmospheric pressure, altitude, and temperature. It had a typical pressure accuracy of plus or minus 0.05 kilopascals, a typical altitude accuracy of plus or minus 0.3 meters, and a typical temperature accuracy of plus or minus 3 degrees Celsius. Using both atmospheric pressure and altitude, the elevation above sea level could be calculated using the equations below. By recording the initial elevation at the start of the ride, the amount the rider climbed and descended during the ride could be calculated using subtraction. To keep the bicycle aesthetically pleasing, we designed a case to hold the MPL 3115A2 barometer and other system components. However, in the case, the barometer recorded bad pressure readings due to the pressure inside the case differing from the pressure outside the case. When tested outside the case, the barometer recorded pressure accurately as normal. The case did not affect the temperature sensor. If time permitted, we would have redesigned the case so that the pressure inside the case matched the pressure outside the case.
A crank arm based power meter was designed for this project, which means that the power being calculated is based on the forces being applied to the bicycle's crank arm. Power on a rotating object is calculated by torque times angular velocity, where torque is the applied force times the radius of the crank arm, and angular velocity is the cadence. To calculate power, a method for calculating force and cadence are required. Strain gauges are delicate resistors that change resistance when force is applied to them. So by measuring how much of the resistance changes when strain is applied, the force can be determined. However, a microcontroller cannot read a change in resistance, so the strain gauges must be put into a Wheatstone bridge configuration to turn a change in resistance to a change in voltage. Also, strain gauges resistance changes very slightly with strain, so the output voltage must be amplified using an operational amplifier to get a usable reading. 4 strain gauges were mounted to the bicycle's crank arm, 2 on the top and 2 on the bottom. Strain gauges are very sensitive and can change resistance depending on the temperature. 2 strain gauges were mounted close to each other to cancel out a change in temperature. 2 strain gauges were put on the top and bottom of the crank arm because when a force is being applied downward or perpendicular, the top of the crank arm will elongate, increasing the resistance, while the bottom of the crank arm will compress, decreasing the resistance. This creates a larger voltage differential in the Wheatstone bridge that can be more easily read. The strain gauges are also mounted orthogonal to each other because one strain gauge will change resistance drastically while the other will not when a perpendicular force is applied, causing an even larger voltage differential. When the strain gauges are wired in a Wheatstone bridge and its output voltage is amplified by an op-amp, the resulting voltage can be read by an ADC of a microcontroller. When force is applied to the crank arm, the ADC values will change proportional to the force applied. Next is a clip from a YouTuber called electronoobs bending a load cell and printing the ADC value to the serial monitor. The readings from the ADC are a meaningless value. It does not indicate the force being applied. Therefore, the power meter needs to be calibrated. To calibrate the power meter, numerous weights are hung off the crank arm perpendicularly and the ADC value is recorded. The changes in the ADC value to the change in the weight should be linear. Cadence is the rate which the crank arm rotates, usually in RPMs. Cadence is usually calculated with a Hall effect sensor or gyroscope. However, this requires extra hardware and even more space on the very limited crank arm. The crank arm already houses a battery, switch, microcontroller, 4 strain gauges, a voltage regulator, and an amplifier. To avoid adding another component, we determine cadence by using the strain gauge data. Measuring the time between 2 peaks calculates cadence. The strain gauge readings are integrated from peak to peak using the trapezoid method for higher accuracy. Converting the integrated readings to a mass and multiplying it by gravity gives us the force. Knowing force and cadence, power can be calculated when cadence is converted to SI units. Since this is a single-sided power meter, the power must be multiplied by 2. To test power and cadence, I tested my power meter with the trainer's power meter. Note velocity should be 0. Because the Garmin's power meter is electrically calculated and mine is calculated by force, some of the power is lost, making my power meter read a little higher. Circuits take much more space than commercially available alternatives. To reduce the size, making custom PCBs with SMD components would drastically shrink the profile. Our design uses larger lithium-ion batteries compared to coin cells commercial products use. To make our design more power efficient, communicating with Bluetooth BLE instead of Wi-Fi would be ideal. The only thing the app can do is read and display data. The app has far more potential and is underdeveloped. And obviously the case for the elevation sensor needs to be redesigned.